In these next series of lectures, we're going to be reviewing Dubins Paths. So in this lecture, we're going to review the waypoint strategies discussed thus far for path management. And then we're going to give a brief overview of Dubins Paths. In the next lectures, we're going to do look into the preliminaries of the geometries that we use inside of Dubins Paths. We'll determine the lengths of Dubins Paths, and then we'll discuss the path manager itself. So let's go ahead and get started. So as we jump in here, just a reminder of where we're at. We're dealing with another path manager, right? So we're still here in chapter 11, but now we're going to do the details of Dubins Paths. So just as a refresher, we're given a series of waypoints, and these waypoints are defined as an ordered sequence of points. And you'll see here that we have a three-dimensional position, and the goal, like we've seen in previous lectures, is just to start at waypoint 1, move to waypoint 2, all the way to we get to the end at waypoint N. And so we've discussed a few different strategies, one of going, well, let's just jump through it. The first was the waypoint switching, and we discussed two sub-techniques within this. One, the idea here is we want to switch once we get to a waypoint. Now, we had a couple different switching strategies. The first was a naive but very simple. It's just switch based on a ball. Once I'm close enough to the waypoint, then let's switch. The problem is if you accidentally miss that ball, or if the ball is too small, somehow you deviate from that. If your trajectory, for some reason, you get blown off course, you never get there, you're going to keep following a straight line, which is problematic. And you need other logic to help you get back on course. Instead, we developed a nice robust switching strategy, and that robust switching strategy dealt with half planes. So we're assuming that, hey, we're at some point going to cross over this line as it's depicted, or a plane because it goes up and down, right? But at some point we're going to cross over that, and we want to then we can switch. So we defined the switching strategy based on that, and we saw that we come in and once we hit that waypoint, we overshoot just a little bit, but then we get back to the path. So just a couple notes that this idea of just switching on a ball is bad. We don't want to do that. Using the half planes, it has some benefits. One, the major one, is that we're going to move through each waypoint. So this is its, well, I was going to say its major benefit, but the next one is good too. So we're going to move through each waypoint. So the aircraft is going to actually pass through the waypoint. So if you care about passing through the waypoint, then this is a decent strategy. Two, it's really quite simple. I mean, it can nearly all be summarized on this slide, right? Where we're just defining, from our waypoints, we define direction vectors. So this is be qi minus 1. This would be a qi. And from that, we can define a normal vector for our switching plane. So here's our normal vector. And then we'll just continue executing the first line until we cross that plane, which we can easily test to see if something's entering the half plane, and then or half space, and then we can go to the next line. So nice and simple. The big drawback is the overshoot. And I'm only going to write this one. Well, so we have overshoot, and I guess two, related to that overshoot, the exact path length is difficult to calculate. And that really they're one and the same, right? Because as we overshoot, we don't know exactly how much we're going to overshoot by. We know we're not going to stay right on our path, and so that path length, we can't just sum up the individual distances between the waypoints. because we're going to be overshooting. So we don't really know our exact path length. Next, we discussed a different strategy. We used fillets for basically smoothing that transition between the lines. So in this one, we come up, we execute the first part of the line. Then instead of going all the way through, right, we executed that arc, and then we executed the final part of the line. And we went through all the math of deciding how to define when to switch, but again, we used that same principle of switching based on half planes, so we have this nice robust switching strategy. And we're utilizing the fact that we know about controllers for both straight lines and circular arcs. So we'll just transition from one to the other, which is fantastic. So we do have a nice strategy here. So if I write up some of the benefits, right? One is that we are using very natural motion. We can stay along this trajectory quite well, right? Because of that, the path length can be calculated. Under nominal kind of low wind conditions, we're going to be able to stay on that path fairly well, right? So we can calculate based on just the two line segments that we're following in that circular arc, exactly how long that path is. The one major drawback here is that we don't go through the waypoints. In other words, we never hit those middle waypoints. And we'll hit the end waypoint, but we'll never hit the intermediary waypoints. So if that's an issue, then this is not a super appropriate approach, right? But do know that we're going to be turning as hard as the circular arc is typically the hardest turn angle possible, and so we do know that we'll get decently close. Okay, so those are the two strategies we've discussed thus far. In this next series of lectures, we're going to be talking about Dubins Paths. So Dubin determined that the shortest path between any two oriented waypoints is going to consist of straight lines and arc segments. And so this you'll see here we have a starting waypoint, right? We have an ending waypoint, and it's oriented, meaning that we have a desired orientation. Well, at the start, we always have a desired orientation, right? But at the end, we have a desired orientation we want to end up at. In this case, we're executing a left turn or counterclockwise. We do straight, and then we'll do a right turn or clockwise rotation. And that'll be using a combination of these circular arcs and straight line segments, where the circular arcs are our minimum radius of curvature. We can find the shortest path between any two waypoints. Okay, so some of the benefits of Dubins Paths is that it moves through each waypoint. Each waypoint. The path distance can be calculated. So because we're using circular arcs and straight lines, we can calculate the distance, and we can follow that pretty well. I'll put calculable. I don't know if that's even a word. Okay. And 3, it will find the shortest path between oriented waypoints. Assuming these dynamics, right? So if we look at this, we have the first two define our position, and then we have our heading angle. And the book now uses this notation of var theta for the heading angle. And v is considered constant. So we have a constant velocity. And for calculating path lengths, we just assume that v is equal to 1. Or when we're commanding the path to be followed, we'll just use our desired airspeed. Right? And so the only input is u. And this is our rotational velocity. And that's in the plane. So this would be in the northeast plane. So about the z-axis. So this is very related to our psi angle, right? So like I mentioned, v is constant. U is going to be in the interval negative some u max to positive u max. So let's write this. U bar is the max rotational velocity. And it's going to find the optimal time, optimal path between two different configurations, assuming these dynamics. Now, to do so, if we look at the choices that it chooses for u, u is actually going to exist. It can be anywhere in that set, right? Anywhere in this set. But it's actually only going to be either negative u bar, 0, or u bar. Okay, so the Dubins path will be our maximum rotational velocity in one direction. So in this case, this would be a left. For executing that left arc, we're going to be in maximum, and that's a negative rotation. So this would be negative u max. The straight line would be u bar is equal to 0, and the right would be that we have u bar is equal. Oops, I put u bar. U is equal to negative u bar. And u is equal to 0. And here u is equal to positive u bar. Okay. So this is how we would execute the path. Okay, some drawbacks. Right? One is that we need to, this is really the major drawback, is that we need orientation at each waypoint. Now, and if you were to look at the benefits of others, the switching strategy isn't quite as simple, right, or straightforward as the previous approaches. Now, this needing orientation at each waypoint, it's not so bad when we have two waypoints, right? That's somewhat normal, right? We have a starting position and we have an ending position, and we have, obviously we're going to have a starting orientation and an ending orientation. But what gets problematic is if we look at our waypoints, we don't care about the orientation and the intermediary orientation. So we don't care about orientation for all of these intermediary waypoints. So somehow we have to decide what our desired orientation is, but we're just given a series of waypoints to follow. So that's really where the drawback of using Dubins paths for moving between more than just 2 points. Okay, so let me write real quick the different possibilities for a Dubins path. And we'll illustrate most of these on the next slide. But we can start off like we've shown here. We have left, straight, right. We could have left, straight, left. We could have right, straight, right. Right, straight, left. So these are all possibilities. The book leaves out right, left, right, and left, right, left. Okay, so we're only going to be talking about 4 of the 6 possible Dubins paths. So that's what this note here is. We're missing 2 cases. So let's talk about each one of these individually, and then we'll chat about this question of why are we missing 2 cases and why is that okay. Excellent. So let's start off on our right, straight, right. You'll notice here that for each of our Dubins paths, when we're designing our Dubins paths, we're going to start off with our particular location and orientation, right? And we call the starting position PS. So this is the starting position. And this orientation of our starting position as our starting course angle, or our starting course angle. So we use chi there. Okay, and then we're going to choose either based on that orientation, we'll go through the geometry of it, we're going to choose one of 2 circles to rotate about. We can rotate about the right circle or the left circle. So in this case, since it's right, we're going to go to the, if we're looking straight along my hand is weird. Okay, we're looking straight along the path, and the right would be off to the right side. So if we're looking straight, it's going to be off to our right side. Anyway, so we follow this circle that's on the right, and then we're going to move straight. And then to get to our end orientation, we'll get onto, we can define again we know where our end point is. So this is our end point and a defined end orientation. Okay. Oh, and I forgot to mention each circle has radius r. So when we're talking about our Dubins paths, what we're given is we have our starting configuration, our ending configuration, and we also have the radius of the circle that we can go about. So those are the parameters that define our Dubins path. Okay, so, and then in this case, when we end, right, we're again turning in a clockwise rotation. So remember that R is clockwise rotation. Okay, so there's another possibility. Again, you'll notice here that we're starting in the same configuration. So case 1 and case 2, our configuration is constant. This is the same in all of these 4 cases, right? So this configuration is constant. So we have the same starting position and orientation, same ending position and orientation. But in this case, we're going to choose, again, we choose to go right and then straight. So very similar to before, although you'll notice that we may have a slightly different diagonal. Then we're going to hit the left circle. So at some point we'll intersect with this left circle and we'll move left. And so this is a counterclockwise rotation. And we use that to get to the exact same end configuration. So that's another possible path. So in this case, we use the right circle, straight, and then we'd use the left circle. Okay. Another possible path is case 3, where instead of starting with the right circle, we start with left, where we're moving counterclockwise. And then we hit the straight line where the vehicle's moving straight. Then at some point, since it's R, we're going to switch to executing the right circle, which is, again, clockwise. And finally, we have our left, straight, left. So we start off left of counterclockwise. we go straight, and then we end on the left, which is counterclockwise. So then the idea behind Dubins Paths is that we have to actually try each one of these out, or calculate the distance required for each one of these, choose the minimum one, and then that's the one we're going to actually execute. Okay, so these are 4 of the major cases. The book is missing 2. So there's 2 other possible cases. We have the right, so we would go around a right circle, and then we'd have left, go around a left circle, perhaps we go really far around a left circle, and then right. And so this would be, let me draw, we'd again have our whoops. We can have our starting configuration and our ending configuration. Okay, so that's one possibility. And another possibility, and I can't draw the same Dubins path going between the orientations, so we're just choosing 2 different ending orientations. So we could do a left, and then, oops, I'll do a small straight because I'm coming up on the other thing, and then we'll do a right. And again, so if I were great at drawing, I would have drawn them in the same exact configuration, but I'm not. So start and P end. What you should notice is that the distance between these are small. So we're just going to be following the minimum radius curvature on all 3, on both of these. I did a straight. So let me redraw that one. We would do a left, right, left, left, right, left. Okay, there we go. Now we'll see that these things are very close to each other. So that when we have a starting and ending point that are really close, then we might use one of these 2 configurations. So this is for when they are close. So if we are assuming that the aircraft is operating in large spaces, which is fairly typical, there's going to be sufficient distance between waypoints to ignore the RL and the LRL cases. So if we just assume that there's sufficient distance, and we will actually review what that sufficient distance is, but if there's sufficient distance, then we don't have to worry about these 2 cases. So aircraft operating in large areas may not care to go between 2 waypoints that are really close together. So there you have it. So we have our 4 of the 6 cases described in great detail and shown in a good example, and then 2 kind of mediocre examples for the other 2 cases. Okay, so there you have it. We're going to be discussing now the geometries of that and how we decide to actually execute a path with the Dubins paths.